Okay, in the previous lesson, we have looked at the circles, and we're going to continue working with the circles. But when we work with right triangle trigonometry and proportional reasoning, we like to consider the simplest circle of all, the circle with a radius of 1, which is also referred to as the unit circle. So here's a portion of a unit circle, the portion lying in the first quadrant of the coordinate grid. In the previous lesson, staking it with portion of the unit circle had been divided into measures of pi over 8 radians. So as done previously, find the coordinates of each of the indicated points in the diagram. Also find the arc length from the point 1, 0 to each of the following. So we're going to figure out the distance by the arc length S. Right? And it says, do not use a calculator. Leave your results as a trig expression. We want exact values. So to find the coordinate of this point, we're going to use, because it's going to be cosine, because it's for x, right? Straight up and down is opposite. So x is side to side, sorry, and up and down is y. So we need cosine of pi over 8. Because the radius is 1, so it'd be 1 cosine pi over 8 or cosine pi over 8. And for the sine, it would be 1 sine pi over 8, which we don't need the 1 since the radius is 1. So it'd be cosine pi over 8, sine pi over 8. And then if we want to know S is going to be equal to pi over 8. Because it's the angle times the radius, and the radius is 1. So that would be the coordinate here. The coordinate at this point, now again, we're looking at x and y. So the x is a cosine, 1 times cosine of pi over 4, and 1 times sine of pi over 4. And then the arc length from here to here would be the radian times the radius, which is pi over 4 times 1. To do this coordinate, same idea. It's going to be cosine of 3 pi over 8, and then the sine of 3 pi over 8, and then the arc length from here to here would be 3 pi over 8 times 1. And then we can go to here, and again, it'd be cosine of pi over 2, sine of pi over 2, and then the arc length is 1 times pi over 2, or pi over 2. And if we think about the coordinate here, it's over 0 up 1. So we can say the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. And we can find that because we know the coordinate and we know the value there. Okay, so now they want us to find the same values using a calculator. So in order to do this on our calculator, we have to make sure that our calculator is in fact set in radians, because this is in degrees, but we're talking about measuring the angles in radians. So if you go under mode and go down to where you have radians and degrees, if you highlight the radians and hit enter, it turns it to radians. And when you go second and do quit, it now says radians. So make sure if you're working with problems where it's giving you degrees, this says degrees. If it's giving you radians, which is going to be what we're going to work with more, make sure this says radians. So now we're going to calculate all those values. So the first value was cosine of pi over 8. So we're going to do cosine, and then alpha y equals gives us a fraction, and we're going to put our pi over 8. Oops. And enter. And the cosine of pi over 8 is 0.92, and I think they told us to round it to 3 decimal places, so 0.924. And then we can do the sine. Actually, sorry. Of pi over 8. And we get 0.383. And then if we do the S value, pi over 8 is equivalent to 0.393. And then we can do this all the way around. So I'm not going to keep putting in the calculator. You should put in the calculator and figure them out. But we can keep doing this all the way around. If we keep doing this, this value is 0.707. And since the x and y should be the same because it's right in the middle. And then the s value is 0.785. And then again, just use your calculator, put the cosine and the sine in, and then the radians in, and get those values to fill out the rest. So then Javier says he's been wondering if his calculator will allow him to calculate trigonometric values for any angle in radians rather than degrees. He feels like this will simplify much of his computational work when he's trying to locate the coordinate stakes. After consulting his calculator's manual, he learns he can set his calculator in radian modes. Now he's ready to examine the following calculations. So then he's calculating those same values we just did up above. So the sine of pi over 8 we said was 0.383. The sine of pi over 4 was 0.707. We haven't done this one. The sine of pi over 2 we had said was 1. The cosine was 0.924, 0.707, and then the cosine was 0. So use your calculator to get the rest of those values, and you can fill in the table. So the coordinates of arc length you found for a point on the unit circle seems to be showing up in Javier's computations. Why is that so? And it says, explain why the radian measure of an angle of the unit circle is the same as the arc length. And so the radian measure is arc length over radius. And on the unit circle, the radius is equal to 1. So if you do arc length over 1, you're going to get the arc length. And that's why they are the same. And then the sine angle in radians is the same as a y-coordinate of a point on the unit circle. So sine is y over r. And then r, in this case, is equal to 1. So y over 1 equals y. And the same thing with x. The cosine is x over r. If r equals 1, then x over 1 would equal x. So based on this work, find the following without a calculator. The sine of 5 pi over 8. So we go back to our rotations. This is 3 pi over 8. This would be 4 pi over 8. 5 pi over 8 would be over here. It would be a reflection of this point. So if it's a reflection, we want to know the sine. The sine value there was 0.924. And since sine is up and down, it would be up 0.924. Then if we can continue to rotate to 7 pi over and to find the cosine of the reflection of this point, cosine is x, so it would be to the left the same value, or negative 0.924. So pi over 8 is over here. It's a reflection of this point, but it's going to be negative. And then cosine of pi, which is straight across, so pi is over here. Cosine is side to side, so over there would be at negative 1. So why are radians important enough to have their own mode on the calculator? Here's some things to think about. We have defined radians as a ratio of arc length to radius. If the arc length and radius are both measured in meters, what is the unit on the ratio? So it would be meters over meters, or centimeters over centimeters, whatever unit is, same top and bottom, so there would be no unit. And so radians is the unit we call it, which is the scale factor of arc length to radius. And so the unit we call it is a radian. If we define radians as the arc length of an intercepted arc on the unit circle with a radius of 1, how does the length of the arc that measures 1 radian on the unit circle compared to 1 unit on the x-axis? So they're going to be equal. Radians are important because they measure angles using real numbers instead of degrees. So why is this important? We're really talking about the idea is we can measure radians on the unit circle by wrapping the number line. So we're actually just using a number line and wrapping on a circle. So degrees are not numerically accurate. They're a measure, a unit. But when we're thinking about radians, it's like measuring the number line. So if we get 0.94, that's 9/10 of 1 unit. So they're measuring in real number values, just what they are would be on the number line. So since we can think of real numbers along the x-axis as a radian measure of an angle of rotation, we can graph sine and cosine functions of x. It helps us to label the x-axis in a way that highlights the real numbers that represents a full rotation, a half rotation, or some other fraction of rotation. Below are 2 possible examples. Graph each of the following, one function per grid. Be prepared to explain your graphing strategy and why you chose to graph it that way. So the first one is 2 sine x. So remember, the number with the x tells us our period. So we're doing in radians. So it's the 2 pi divided by 1, or 1. The period would be 2 pi. So we're going to start at 0, and we're going to go to end at 2 pi, which means halfway in between. We're going to be back at pi is also at 0. The amplitude is 2. So in between that, we're going to be at 2, and then up 2, and then down 2, and then up to the middle. Then up 2, down 2, back to the middle. And then we continue that this way, down 2, back to the middle, up 2, back to the middle, down 2, back to the middle, up 2, back to the middle, down 2. And that would be the full cycle of the graph. For this one, we're going to take 2 pi and divide by 2, so our period is just pi. So we start at the middle, we go 1 period, halfway in between is back at the middle. Our amplitude is 1. So we're going to go in the middle of these 2 points up to 1, in the middle of these 2 points down 1. Up 1, down 1, up 1, down 1, or sorry, up 1, down 1. I gotta tell myself, down 1, up 1, down 1. I'm getting a little uneven, but you got the idea. And there's our cycle of sine 2x. We're going to skip the ready for more. You can try it if you want. And so takeaways. Every point in the unit circle gives the sine and cosine values of an angle of rotation because the arc length of an angle of rotation measures the angle of rotation in radians. The x-coordinate of the point gives the cosine value of the angle of rotation. The y-coordinate gives the sine value of the angle of rotation. And the unit circle defines trigonometric functions over the domain of all of real numbers, because the real number line of unit equal to the radius of the unit circle can be wrapped. So basically we're wrapping the real number line around the circle. And that gives you the radian measure. So a radian is just how far it is on a number line. Okay, so then the retrieval is asking us to write equivalent expressions by rationalizing the denominator when appropriate. So we don't leave radicals in our denominator. You should have learned that at some course in the past. So to rationalize a denominator, because it's a square root, we need 2 of a kind or a perfect square. So if we multiply the 7 by 7 again, we have 7 squared. So we get rid of the radical. And whatever we do the numerator or denominator, we have to do the numerator. So by doing this, this is equivalent to 1. We are not changing its value. but we're getting rid of the radical in the denominator. So 2 times root 7 is 2 root 7. And then the denominator, root 7 times root 7 would make root 49, or root 7 squared. And that square will cancel, and we just have 7. So the idea of getting rationalized in the denominator is to get rid of the radical in the denominator. This problem here, we're going to rewrite this so we don't have a double fraction. So root 3 over 2 is a numerator. When we divide by a fraction, we really multiply by its reciprocal. So we're multiplying by 2 over 5. Since we're dividing by 2 and then multiplying by 2, those 2's cancel. We end up with root 3 over 5. Now we want to change our angle to radians. So we have degrees. To get rid of degrees, since it's in the numerator, we got to put the degrees in the denominator. And since 180 degrees is equal to pi, that's our conversion factor. We're going to end up with 80 pi over 180. We can simplify the numbers. 80 and 180 can simplify, divide by 10. We get 8 pi over 118. And then we can divide that by 2 and get 4 pi over 9. And this one, again, put it over 1 times pi over 180. 135 pi over 180. Those are both divisible by 5. So 5 goes into 135, 27 pi. And 5 goes into 180, 36. And then those are both divisible by 9. So we have 3 pi over 4. And then the last two, if we want to convert from radians to degrees, again, the conversion factor, since we have pi on the top, we got to get pi on the bottom, so it cancels, and it's 180 and pi are equivalent. So this is like multiplying by 1. And if we simplify that, the pi cancels, and then we get 4 times 180 over 3. 180 and 3 simplify to 60 over 1. So 4 times 60 is 240 degrees. And this one would be times 180 over pi. Again, the pi's cancel. We have 17 times 180 divided by 9. 180 and 9 simplify to 20. 17 times 20 is 334. Sorry, 17 times 20 is 340.